Hello ladies and gentlemen, you are welcome to this channel. Today we shall be discussing chemical reaction engineering on the topic of reactor design. Chemical reaction engineering is a study of chemical kinetics and reactor design towards production of economical and desirable product. To perform a reactor design, you need to know the reactor, the system boundary, and system volume. So the reactor can be the container, the boundary of the container of the reactor itself, or it can be an arbitrary volume that you choose around the boundary, the original boundary. So the purpose is to know when the species J goes in and when the species J or where the species J goes out. So whatever is around the frame, around the reactor, or where the entrance and exit are, is the system boundary. And whatever is contained within the boundary is called system volume. So to continue, we need to perform general mole balance. General mole balance is to define how the species goes into the system volume and how it goes out of the system volume and how it is generated within the system volume. So we define the general mole balance as what? The Fj naught, the rate of flow of J into the system volume, minus the rate of flow of J out of the system volume, and the generation of J within the system volume is equal to accumulation of J within this volume. Please take note. This is what goes in, this is what goes out, and what is generated is within, maybe by reaction or some other things. What is generated about J is within the reactor. And what is accumulated is also within the system volume, the Nj dt. So we represent Fj naught to be what goes in, Fj to be what goes out, generation with Gj, and accumulation within the system volume to be the Nj dt. So in summary, this is Fj naught, inlet, Fj outlet, and Gj, the generation within, and the Nj dt as the accumulation of J within the system volume. Let me explain this generation term, Gj. Gj refers to generation by reaction or by some other means within the reactor system, and is defined as Rj times V. That's the rate of reaction of J multiplied by the volume of the reactor. But at times, within the reactor system, within the reactor volume, the rate of generation may differ. Maybe it is faster here, it is slow here, it is different here as well. So that means we have a kind of distributed, we don't have a uniform rate of reaction for the species J. So within the volume, it varies within this area, this area, this area. In that case, we are going to have a kind of summation of all of the reaction rate of J differently. So if that happens, then we are going to have our general mole balance to look like this. So it will be an integral throughout the volume of the reactor. So now let's look at batch reactor. In batch reactor, we have a system like this. Nothing goes in, nothing goes out, only what is put inside the reactor initially. So, and it may be stirred or not stirred, that is, it may be mixed or not mixed. So, in this case, it means for the batch reactor, there's nothing goes in, it's zero. There's nothing goes out, it's zero during the reaction, nothing goes in and nothing goes out. So, we only have the reaction within the system and the accumulation of the species J. So, in that case, we are having Rj dV equals to the Nj dV. So because this cancels out. So if that happens, but if it is well mixed, in which case the rate of reaction everywhere is the same, therefore we can remove the integral and have Rj times V equals to the Nj dt. So this stands for the reactor design equation for batch system. The continuous state tank reactor, CSTR, is a type of reactor whereby species goes in and species goes out, and it is well mixed. So normally it is operated at steady state. And what does that mean? It means there is no accumulation once the steady state is reached. It doesn't mean there's no accumulation at the beginning, but once it reaches the steady state, when everything is uniform, then there's no accumulation of species J again. So that means in the general mode balance, our accumulation time is 0. Similarly, there is no variation in the spatial, because it is well mixed, there's no spatial variation in the rate of reaction. In that case, we have our Fj naught minus Fg, and we remove the reaction term, the generation term, from the integral. So as a result of that, we are going to have the reaction equation rearranged like this: Fj naught minus Fj all over minus Rg. So this is a reaction whereby you can determine the volume of the reactor necessary to reduce the flow rate of species J from Fj naught to Fj within the reactor system. Tubular reactor is another type of reactor, also called plug flow. It looks like this. The species J goes into it and it reacts along the length of the reactor, So it varies along the length of the reactor before it goes out as Fj. To perform a reactor design for this kind of reactor, we often take a subvolume like this. We cut a volume out like this. And if you cut it out, it will look like this. So it looks like this small cylindrical tube that is cut out. So we can see the thickness of what it cut out is delta Y, the volume of the subvolume is delta V, and the surface area at the face here is A. So if you want to see delta V, which is the volume that we cut out, is equal to area times delta Y as thickness. So how do we perform the general mode balance here? We don't follow, we actually observe this actually, but it doesn't follow the general format precisely. So we have to look at what enters here is Fjy, and what goes out here in the subvolume is what? Fj y plus delta y, and what we have inside that place is Rj delta V. We believe that in the small volume we cut out, the reaction or generation of J is uniform. So, and let me say, it is also operated as steady state, just like the CSTR. So therefore, it means the accumulation time is 0. So if we rearrange this in a derivative form, it will look like this: Fj y plus delta y minus Fj y divided by delta y is equal to what? Minus Rj Arj. Remember I said A delta y, delta V is equal to A delta y. So that is why we have A and delta y here. So this one looks like a derivative form in calculus. And as a result of that, we are going to have minus Arj equals to dFj dy. So minus dFj dy. So if we have that, so that means that we have dFj dy equals to minus Arj. We can still combine minus Arj. So we can still combine our A and dy to give us dFj dV is equal to this minus. So minus we cancel minus to give us positive. Then the Fj is equal to Rj. So to determine volume here, we can define volume of reactor to perform a particular conversion. we can have dV is equal to dFA over dFJ over Rj. So that is the design equation. The last type of reactor we are going to consider is packed bed reactor. So to design for packed bed reactor, let's talk about what it is actually. It's actually like a tubular reactor, but instead of an empty or low tube, we have catalyst filling all the spaces inside the reactor. So the reaction actually takes place on the catalyst. Unlike in the tubular reactor, it takes place in the volume of the reactor like this for the tubular. But in this place, it takes place on the catalysts that are loaded inside the reactor. So the design equation looks similar. So like this one that we have, dFA dV is equal to Ra. In this case, we only have dFA dW equals to Ra. So what is the W? W is the weight of the catalyst. This V is the volume of the tubular reactor, but W here is the weight of the catalyst embedded in the reactor. So that's just different. They are very similar. So I believe with that you have understood how to set up design equation for each of the popular reactor system. Thank you.